Hi everyone, my name is Ashmi Banerjee. I am a PhD student at TU Munich and I will be sessioning the chair today on optimization and evaluation part 2. So in this session we will have 6 spotlight papers which are 5 minutes each without any Q&A, and if you want to ask questions you can go and ask them at the poster session later. And we will have 2 reproducibility paper, 10 minutes each, where you will have the chance to ask questions either through Slido or through in-person questions. So yeah, let's get started. So the first paper is titled DNS-Rec, Data-Aware Neural Architecture Search for Recommender Systems, and the speaker is Maolin Wang. Thank you.
Hello, hello everyone. Today I will show you our new work, DNS-Rec, Data-Aware Neutral Architecture Search for Recommender System. So the presentation includes 3 parts: background and motivation, framework, and experiments. So in sequential recommender systems, most existing attention-based models exhibit substantial computation overhead. How to solve this problem? There are 2 different directions. The first one is network pruning, and the other is network architecture search. But existing methods have some limitations. First, they rely on static strategies, and second, they fail to adapt to dynamic data environments. And the last one, they always lead to suboptimal model performance in practical. To solve this problem, first we propose automatic pruning methods for resource-constrained architecture search. And to solve the second problem, we propose effective NAS methods with data-aware gates. And to solve the last problem, we specialize model structures with dynamic resource-constrained strategies to find a balance between resource consumption and accuracy. So then we talk about our framework. Overall, we have 3 different components: SuperNet, B-level controllers, and data-aware NAS. And we use 2-stage process to train our model. So first, we embedding items and their position information to representation. And we use a linear attention layer to reduce the computational cost of attention layers. Then we stack the transformer layer to construct SuperNet. Then we talk about our B-level controllers. The first level is transformer controllers, aims to search for an optimal dimension. And then we have a deeps controller. This controller aims to find the optimal number of transformer layers. And then we propose a data-aware NAS to preserve the input data bunch and inject it to transformer layers. You can see this equation and finger. And finally, we use a dynamic resource constraint and optimization. We propose a dynamic resource constraint as a initial term, and we use flops to measure the resource consumption. Then we optimize the flops loss directly. We use a bunch of data to update model weights and architecture parameters. Then we talk about our 2-stage process. In first stage, we use the data-aware gates and B-level controllers to reduce the computational complexity. And in the retraining stage, the network is reconstructed based on well-learned model weights. Then we talk about our experiments. So this is our experiment setting, and I want to highlight this. So our methods balance model complexity with test-specific performance. And then you can see we have efficiency experiments. So DNS results in extended training time, right? Because we need to search within the SuperNet. but we have a more lightweight structure and shorter inference time. So DNS-Rec has superiority than transformer-based models with linear complexity when inference on a larger dataset. And we also provide a parameter analyzed, but due to the time limitation, if you are interested, you can see our original paper. And finally, we summarize our works. We introduce data aggregate methods and dynamic resource constraint strategies, optimizing compact architectures for SRS models. We reduce the computational demands of SRS model while maintaining high performance, and we do some experiments to show our method's performance. So if you have any questions, please feel free to contact me with this email. Thank you for listening.
Thank you very much. So let's welcome the